Now before discussing about threads, let's see what has happened with these processes. Okay, so when we have seen that, one thing is clear: whenever you want this parallelism, we are going to go for multi-programming. So multi-programming is a concept in which we have only one CPU, but then we'll be able to perform many tasks at the same time. I mean, it appears as if many tasks are being performed at the same time because we are having many processes, and all these processes will be switched. So one process will execute for some time, and then next one, and then next one, in a round robin fashion, right? So till now, only type of parallelism we are able to get is through the use of multi-programming, right? But then the multi-programming has got some disadvantages. The disadvantage is like whenever you want to switch from one process to the other process, because you have only one CPU, it is going to incur some cost because of the context switch. Therefore, multi-programming is an expensive task, right? But then multi-programming has an advantage that each process can perform something individually. But what if our need is we don't want to perform some independent tasks, we want to perform the same task over and again. For example, we have seen something called web server. In web server, everyone will ask for the same web page, right? Therefore, the code required to service a client is actually the same, even if it is client 1, client 2, or client 1000, right? So in that case, going with multi-programming, right, is a disadvantage because we don't have different tasks, we have the same task and the same code. If you are going for multi-programming by using various processes to service various clients, then you unnecessarily you have to create a process in which the same code will be there. Okay, listen to this, I'll just show you here. Now assume that there is a web server running, okay, and this web server is a process, and if you look at this process in the memory, it will have all this, right? So one is the code and other is the data, right? And we know the other parts. One is stack, other is heap. So apart from this is what will be present. These are all will be present in the memory. Apart from this, the process will also get, in case if it is opening any files, it will also get something called as file descriptors. So what is a file descriptor? It is a programming language terminology. Generally, file descriptors are used to access a file. So once you open a file, then you are going to get the file descriptor. Generally, every process will have certain files open, right? And then apart from whatever I have shown here, you are going to have something called as resources which will be allocated while it is running at the CPU. So one such resource you can think of it as register files, right? Register file means the register set that you are going to get. Got it? So everything is applicable for one process. Now when we are going to create and also we are going to have program counter, isn't it? So these two are something which will be allocated for a process, and these will be used while running. If the process is not running, these things will be saved in something called as context of the process. And if you want to run a process, you are supposed to load these things into the CPU registers as well as CPU program counter. That is what we know about the context switching. We already discussed about it, right? So whenever a process is running, the next instruction will be pointed by the program counter, and whatever registers it is using, they all will be present in the register file, right? In case if it is not running, you are supposed to save all this at some place so that later we can get it and run. Got it? So anyway, these are also associated with the process. Got it? When it is running. Now let us say this is a web server whose purpose is to service a client whenever he needs some web page. Let us say it is currently processing one request, which means it is sending the web page to a client. At the same time, if some other client comes and asks for this service, then it will not be able to provide this service. Then what are the various alternatives we have? One good alternative is create a child process and then assign the work to the child process, right? Therefore, if this web server uses fork system call in order to create a child process, the child process will also be exactly same as the web server, but this is a parent and this is the child, right? Both will be having different process IDs. Now whenever you create it, exactly the same memory image will be created as I told you earlier, right? So what will the memory image contain? One is the code, right? And the other one is the data, and the other one is stack and heap, right? And the other one is whatever files are open here, you are going to get the same files, and associated with this will be register set and the program counter, right? And the program counter initially when it is created, both will be having the same value, right? And also register files will also be having the same value. Now if you observe it, if you clearly observe it, this part is same, isn't it? The data and the code section are exactly the same. Now if we want to execute the same code, why do you want to have two copies? And second thing is, whenever you want to switch between these two processes, context switching is required, which is very expensive. Got it? So what are the disadvantages of this? If you are looking at this multi-programming using processes by creating new process for any new request, the problem is that it is expensive because of the context switching, and then resources are also wasted. See this, same files are opened, same file descriptors will be again copied, and even the same data, same code will be present, and these will also be same, but later they will change anyway, but initially they will be same. So everything is exactly the same. So one thing is, CPU wise it is expensive because context switching is required, and memory wise it is expensive because memory is unnecessarily wasted to store the same code and same data two times, right? So this problem is being solved by using the threads. Now let's discuss about the threads. So whenever we talk about a thread, instead of using the name process, we use the name task. A task is nothing but certain amount of work that we want to achieve, and we are trying to achieve it using multiple threads. Okay, so this is probably the first time you are talking about or you are listening about threads, so just be careful. I'll discuss what it is. Now initially when you start a task, it will have only one thread. Okay, now let us say this is a web server task. So if someone has to be served, if a client has to be served, then what is that we are going to do is, we will be running one thread, and this thread will be servicing this client. Now exactly like a process, this will have the same thing. One is code and other is data, and the other thing is we have the heap data as well. Okay, but then what happens is, every thread will have its own copy of stack, right? And also data as well as heap will be there, which will be shared. So this code and data section will only be once, right? So it will have its own copy of the stack and its own copy of the register set and its own copy of the program counter. Now suddenly if someone else asks for a new request, then instead of creating a new process like in that method, we'll try to create a new thread. Now the advantage of this, let us say we are talking about user level threads. So there are two types of threads. One is user level threads and the other one is kernel level threads. We shall discuss about the difference between user level threads and kernel level threads later. But for now, let us discuss about the difference between the processes and the threads first. In this case, we are talking about user level threads. Now, what happens is if we get suddenly, see, one request is currently being processed. We got a request and that is being processed by a thread. Okay, what is a thread? A thread is nothing but a sequence of execution, right? So you can consider a process, in this case this process, as a task with a single thread. Got it? So what is a thread? A thread is nothing but a sequence of execution. That's it. And sometimes thread is also called as lightweight process. Lightweight process means it is not as heavy as a process. Okay, so actually it will contain everything that a process has, but it is not that heavy. That heavy means if you see this, every process will have its own copies, but threads will be sharing it, as I will show you. Now assume that when client 1 is being serviced by this thread, let us say client 1 is being serviced, we got a request from client 2 for the web page. Then in general, if you don't have this threads execution, if you have only web server, right, let us say you have only one web server and we are not even creating the child, then what happens is we have to wait until this entire request gets fulfilled, then only we can take the next request. But in case of multi-threading, the user can create a new thread, right? So mark my words, the user is creating the new thread. That is why it is called as user level threads. In this case, if you have to create a new process, you have to call the system call, and therefore our operating system will create a new process. That is why it is expensive, because operating system is involved. It is cheap because operating system is not involved and user is actually creating the new process, right? Therefore, new thread. So one more new thread will be created, and it will have its own stack, it will have its own register set, and it will have its own program counter. Now having two different program counters will enable the thread to remember where it has stopped earlier, right? Now what we do is, for some time this process will run this thread. Let's call it as a task. For some time this task will run this thread and then it will switch to the next thread. Now again, for creating the thread, we are not calling the operating system, and also from switching from one thread to the next thread, we are not calling the operating system. Therefore it is very inexpensive. So just like a process, a thread will have all these states, right? So new state, ready state, running state, block state, as well as terminated state. Everything is same as a process, but only thing is all the resources are shared. So data will not be unnecessarily copied two times. Code will not be unnecessarily copied two times. You can create any number of threads and all of them will be sharing everything, including files and signals. Files will also be shared, right? So that is the advantage of the threads. So what is the main difference between the process and user level threads is, you can think of it like this. Let us say we are using the processes using fork call, right? So instead of, whenever we want to do multi programming, we are going to use this, right? So if you want to achieve the parallelism using the processes, we are going to use fork, right? And the other one is threads. So in this case we are talking about user level threads, right? So what is the main difference between these two? We shall see it. So one difference is clear. So in this case, system calls are involved. So system calls are involved for creating a process, isn't it? fork is involved, and in this case no system call, right? And in this case, if you have to switch from one process to the other process, context switching is required, right? So in this case, no context switching is required. So simply register set switch. So register set switch. So in most of the cases, even this register set is going to contain the program counter as well. That is why I am not saying program counter switch also. If you change the registers, program counter is also a register which is a part of the register set file. You can include it there. And now register set will contain something called as stack pointer, which will point to a new stack. Therefore you need not switch the stacks explicitly. Once you switch the registers, automatically stack will change and program counter will change, right? Therefore it is cheaper, isn't it? So what can you say about this? This is expensive, this is cheap, and this is expensive, and this is cheaper. Got it? And if you see it, even at the memory level, right? So different copies, of code and data. Code and data section are required here, right? But here we have same copies. Same copies of code and data, right? So now we are having only the same copy of code and data here, right? But then here we are having different copies of code and data. But then there is a problem here, right? So it is not a problem, you can think of it this way. See, here whenever all the threads are executing or using the same address space, then what happens is every thread will have the access to other threads stack as well as to the data as well as to the code. Therefore we might get some synchronization issues. So in threads, if you have to share some data, or if you want to use the same code, then we might have to use something called as critical section, isn't it, or locks. So critical section or locks are required in case if your threads are going to share it. But in this case, if you want to share information, if you want to enable inter-process communication, here also we don't have any other option. We have to use critical section and the locks. That is why I am not writing it as a difference, because either in threads or in processes, both the critical section and locks concepts will be required if they want to communicate. But then one advantage you have in having different processes, one process will not be able to change the stack of the other process. Both are completely independent. There will be no interference at all. But then here if you observe it, one thread can access the stack of the other thread, right? It looks like it is a problem, but then it is not a problem because we don't have to provide any protection, because both these threads are actually created by the same user, and the user is going to have control over how a thread is going to execute. Why will a user, when he created two threads, will write the code in such a way that one thread will corrupt the other? Therefore no protection is required here. Therefore it is not at all an issue. So if you see anything, there will be only advantages in threads compared to the processes, right? So this is why we need threads compared to the processes. So there are some disadvantages as well. So when you look at this user level threads, there is a disadvantage. Sometimes what happens is, let us say this particular thread wants the hard disk, and so it has called the operating system, some system call related to hard disk, and then that system call has blocked this thread, right? See, now for a operating system, it doesn't know that it is a task and it is having these many threads right? So all these threads are being created by the user library at the user level. Therefore our operating system, the kernel, is unaware of this threads concept because it is implemented at the user level. Now for a operating system, this entire thread might look like, this entire task containing many threads might look like a single process, right? And assume that this particular thread, it wants some service from the operating system. Let us say in this case it is asking for the hard disk. Then this thread will make a request for the system call, through system call to the operating system, asking for the hard disk. Let us say hard disk is not available now. Then operating system will block this particular thread till hard disk becomes available, right? But the problem is, whenever this particular thread is blocked, according to operating system, it is not a thread, this is the entire process. So even when one thread gets blocked in the user level threads, the entire process will get blocked. But if you look at these two processes, if one process gets blocked, the other process can execute, because to the operating system they are two different processes. Therefore it can schedule the other process even if one process is blocked. But here to the operating system, it is a single process, it is unaware of the threads, right? And so what happens is, as I told you, one thread, if it gets blocked, the entire process will get blocked. That is a disadvantage. Therefore the parallelism may be affected in case of threads sometimes whenever there is a blocking system call, and this one can be rectified by using kernel level threads, right? So what is kernel level thread is, instead of asking a user to create the threads and then switch between the threads, we'll ask the operating system to create the thread and switch between the threads. But then it is going to introduce its own set of problems. What is it? For every creation we have to again call the operating system, right? Okay, so that is called as kernel level thread. And also if you see, when you are having three different threads executing, if the operating system sees it as a single process, it will not give it 3 time slots. It will give it the same time as the time given for a process, right? Let us say one process is having 100 threads and other process is a simple process which is having only one thread. Now if these are user level threads, then according to the kernel, it will treat both of them equally and it will give the same time for executing this one as well as this one, right? In case of user level threads, that is why we know there is a concept called as kernel level threads, in which these problems have been eliminated. Now we shall see what that kernel level thread is and what is the difference between user level and kernel level thread. Okay.